Hello, it's our pleasure to have with us Professor B. Vishwanathan. He is Professor Emeritus here in IIT Madras. He was a faculty here at IIT Madras for almost 35 years, so which is a very long time, much more than the age of most postgraduate students. He's the author of numerous books. He's considered a very important expert, a very well accomplished expert in the areas of catalysis and energy, amongst other areas in chemistry. So he has contributed in many ways to the development of science in our country. He serves in many important committees which make key decisions on what projects should be funded and so on. He has also served in the United Nations Development Program Committee for looking at funding activities in the area of catalysis. And so he's both a national as well as an internationally accepted expert. His areas of research include electrochemistry and catalysis, so that covers areas such as fuel cells, batteries, and hydrogen storage, just to name a few. And over 35 years, numerous students have completed MS and PhD under the guidance of Professor B. Vishwanathan. And they hold fairly important positions in many industries, many national organizations, and so on. So it's really our privilege and pleasure to have Professor Vishwanathan with us. And I'm sure the views that he has, that he's going to share with us on research in chemistry, would definitely be very beneficial for all of us. So thank you, sir, for joining us.
Thank you.
So I would like to start by asking you this. In engineering, I'm sure even in chemistry, which has been around for as a field of science, as a recognized field of science for a very long time, are there still areas that are considered, old, traditional areas of research in chemistry?
Yes, there are few areas of chemistry which are old, but still it has a relevance to even today. There is one of them is the synthetic organic chemistry. The synthesis is always associated with organic chemistry, but today it is no longer synthesis in organic chemistry, synthesis of chemicals. Okay. So therefore, the inorganic chemicals or even industrial chemicals, how they can be economically synthesized and also produced. That is the reason. Second thing is, science itself today has changed its face. Science, in the conventional way, we were looking at the basic problems. Today, the science has to be delivering materials. Materials means, for example, you take a cell phone, it is a material called dielectric resonators. So this is a simple material, a perovskite. So therefore, this type of materials have to be designed and fabricated with very specific properties. Dielectric constant has to be a specific value. The temperature quotient of dielectric constant has to be very low, like that. So this is one of the examples. There are many materials. Even, for example, you take solar cells. Solar cells today is based upon silicon solar cells, but silicon being a very important material and also costly. So the design of new solar materials are coming. Silver based solar cells and other things are cheaper than the silicon in the manufacturing process. Cost process, silver may be costlier than that, but in the solar cell manufacturing thing, it can be cheaper than the silicon solar cells. So therefore, any area if you take today, chemistry is, I will say, energy, materials and environment. These are the three main areas which are evolving in chemistry. But it doesn't mean that the customary areas of synthetic organic chemistry or synthetic inorganic chemistry, they are also still important. For example, in synthetic inorganic chemistry, metal organic frameworks, which is just like a palace. Okay, but only thing is, it is a palace in chemicals, not a brick and mortar. So these type of metal organic frameworks, mesoporous materials, they are all the new generation materials. They have very great advantages and also utility. They can be used in the many industries. For example, today if you take the oil industry, it is, even though oil is the main product and the refined oil is the main product, the conversions are taking place only because of these materials. Previously, the zeolites were used, now mesoporous solids and these MOFs and things, essentially porous solids are being used. Why we are using this is now refining is based upon bottom of the barrel. We are not taking the crude which is on the top of the layer, because it is, when you go to the bottom, the hydrocarbons are long chain hydrocarbons. Therefore, they have to be cracked. Previously, it was not so long a chain, but previously also long chain, but 30-40 carbon atoms. Now 100 to 200 carbon atoms. So therefore, the cracking or the refining. Okay, refining means making the crude oil into useful products. So this requires porous solids of very high porosity, very high pore diameters and other things. These solids have to be fashioned, designed and fabricated. So this is the new generation. In the same way, energy conversion and energy storage, these are the two new areas of, I will not say new area, but newly finding acceptance. Now the storage is a very important thing. Energy conversion is it may be possible by the chemists, but the storage is a very important problem. The storage must be in such a way that the economy must be equal to the petroleum oil or petroleum price. We will simply take fuel price. Now if it is not only fuel price, but fuel, for example, if you take a car, it takes 50 to 100 liters of petrol. So therefore, if we are storing the fuel, we should store equivalent to that, so that you will be able to travel 500 kilometers or 600 kilometers at a stretch, instead of the intermediate storage thing. So this is a main area of research today in materials for energy storage. In chemistry and physics, these are the two immediate areas. The third thing is, in designing these solids or materials, we have to know functionalize them. The functionalize is, for example, if you take a solid, there are 10 to the 15 sites, out of which only 10 to the 12 or 10 to the 10 sites will be active for all of them. How to make those 10 to the 10 as active sites and how to keep them in the active state. This is a very important thing, because chemists are always using the molar quantities. Molar quantities means 10 to the 23 molecules. So therefore, we can easily analyze them. Whereas when you have to analyze 10 to the 12 or 10 to the 15, your molar concentrations becomes nanomolar, picomolar, or even lower than that. So the analysis and identification and its structure and all those things is a very important area. So this is another important area of research in chemistry. I will say is generally science. The another development that has happened in the last 10 years is how to predict them. How to a priori you have to design a material, or you have to say this is the material has to be designed. So this is called today is theoretical chemistry. You can say computational chemistry, whichever way you want, modeling chemistry, whichever way you want to do that. But computation in chemistry today has taken a new turn, which is called the density functional theory. Density functional theory takes from the basis. Okay, for example, why hydrogen is present as H2? That is because of the 1s electron of one hydrogen combines with another 1s electron of another hydrogen, making a covalent bond. So therefore, we know now hydrogen cannot exist in the normal conditions as a hydrogen atom, but it can exist only as a hydrogen molecule, because the energy of the hydrogen molecule is lower than that of the energy of the hydrogen atom. So the same way we can now make this thing for materials. So in the olden days, the number of atoms in a molecule was very small, maybe 10, 20, maybe 100, let us assume. But today, for example, metal organic framework, there will be thousands of atoms. So therefore, we have to minimize the energy and predict them. So this is done by density functional theory or self-consistent field theory or artifact calculations. But the recent times, density functional theory has overrun all these other things because of the time involved in the computation and also comprehension by the chemist. Okay.
Okay.
Because the artifact or self-consistent theory requires a tremendous amount of mathematics. This density functional theory is only gross, but there are other approximations, but this is the highest approximation that is possible today. So this theory has taken over the thing, and many chemistry laboratories are now facing the problem of how to apply this to their materials. So therefore, what has happened here is in the chemistry, the research has taken a new turn. It is not enough if you are very good synthetic chemist. You are not. If it is not enough if you can to make use of the tools to analyze them, but you should also be able to predict them.
Okay.
So this is the changing situation in chemistry research today.
Okay. So that's a very, I mean, I think a lot of detail you have told us about both, I think, traditional areas of research and where, research is heading in chemistry these days. If I go back a little and let's say look at the set of students who probably join a chemistry department for an MS degree or a PhD degree and so on. And you have interacted with a lot of them. They come from a variety of different institutions where they would have done, a bachelor's degree, a BSc, a Bachelor of Science degree maybe in chemistry and so on. And then before they join here for a master's degree or a PhD degree. So in general, in their preparation as they come in, do you see that there are any specific significant challenges that these students face when they try to join, I mean, when they get into a master's or a PhD degree? Are there certain areas that maybe their preparation in general tends to be a little less, for which, after they join, they are required to pick up more, maybe more courses or have some more preparation in those areas? Is there some lacuna in terms of, either theoretical learning that they have or experimental experience that they have in what you have seen?
Yeah, that is a necessary thing, especially with the Indian context, because as I told you, analysis has to be at the atomic level today. Previously, analysis is on the millimolar or micromolar. Now it is not that way. We have to, single atoms have to be identified. So this type of techniques that are available today, for example, XPS or UPS or any other technique, we will not to go into all the details. That is, the analysis must be the probing system also atomic level, the probed system also at atomic level. So therefore, this means this knowledge is not available in Indian universities. So therefore, the students who come for research, but they have to use them, because if they have to be competitive in research in today and publish in very high impact journals, or impact is not a correct thing, in high journals, then they have to be using these techniques. There is no other way out that. In the same way, as I told you, theory also is a lacuna here, because computing facilities in many universities are not so high. So they might not have learned these things. Even if they have learned, they may not be able to use them in the actual sense, because the programming is a bugbear for many of us, because we are not professional programming people. So now what has happened is the second thing, that is, I will not say the students have become or the past students are brilliant, the present students are not brilliant, and that is not the criterion. The criterion here is, today the diversions for the student is very high compared to the diversions that you and I had. Okay, that is why the students, when their attention is diverse, then they are not able to concentrate.
So attention spans are less these days, relatively, generally speaking.
Yeah, that is what is reflecting as though the students are a little behind, but otherwise the capacity of the students remains the same.
Okay.
Only thing is because today the computer is there, and I think they can use computer for learning. Instead of that, they are using it for playing. Okay. It's one of them. But in chemistry, computing usage is only to the limited extent. That is should be improved.
Okay. So generally, people have not been using it as much in the computational sense.
That is one thing. Second thing is, even for search, as a search tool, they can use only Google and all those things. That is not enough now, because the literature is so high. So because even if I were to tell you, I have been recently writing a book on carbon dioxide to fuels and chemicals, because we know very well fuels and chemicals can be used to produce carbon dioxide. But
okay, so the reverse process.
Reverse process. So therefore, that means we are closing the cycle. So that so this literature in the last 10 years is enormous.
Okay.
Okay, that is how to convert. Even though we have not succeeded still. Succeeded means in the manufacturing level, but we have succeeded level in converting few molecules, few molecules of CO2 into chemicals, useful chemicals. But this knowledge must be known to them. Then only they will be able to take up the challenge and do them. This is only one example. Another example is, as you have already said, is fuel cells. In the case of the fuel cells, the problem it does not exist with the electrode. The problem exists with the electrode at the oxygen reduction, not on the fuel combustion. So therefore, designing proper oxygen reduction electrode is the question here. Up to now, we have been using only platinum based electrodes, but now we can use many other materials. One of them is heteroatom, nitrogen, phosphorus, sulfur, boron substituted carbon materials can be easily used for the oxygen reduction reaction. It can be comparable, not exceeding the platinum, but it is already comparable with the platinum today. With respect to time, it will be improved. Then it will be cheaper electrode and the fuel cell will become a reality. So the second thing is, as I told you before, the storage. Storage also is a very big issue. For example, supercapacitors. Okay, instead of batteries, because battery is a weighty substance and things. So supercapacitors. Supercapacitor also is a possible means of energy conversion device. But only thing is materials is the question. Now in the material that we are now using is carbon materials or carbon based materials. We will not go into the details of it. So, but we have to innovatively bring out, as I told you, carbon materials with these heteroatoms, and also structurally they should be made more stable. Carbon materials are layered materials. Maybe layered materials are possible to use as supercapacitors, but chalcogenides, dichalcogenides, or sulfur containing or phosphorus containing, all these things will be in the future will be new supercapacitors. Like that we can go on talking about it, I mean the materials in the catalysis or NEC. So therefore, what today is the students, research students should be able to focus on these new materials. And since they have been conventionally taught, they are not able to think the new materials sense.
Okay, so a lot more reading up is required to catch up on materials that are more recently being looked at and picked up. Okay, so of course you already mentioned a lot of examples of where maybe there's a direct industry application, and certainly petroleum industry is one that you were talking about. Generally in MS and PhD degrees, we tend to think of research which is significantly ahead of its time. So in this context, from a PhD, MS PhD kind of research activity that takes place, where do you see industry interest in this kind of in a research program kind of activity?
Okay, in the industry, since we are dealing with our center is dealing with refining industry, there are, as I told you, we are today refining industry, because refining industry is a major industry in India. Nearly 15 refineries are there and all those things. The refining capacity, even though increased, the refining material, the crude oil, is the bottom of the barrel. So therefore, the conversion to useful chemicals is a big problem. Not only useful chemicals, even the waste chemicals that come out, okay, for example, tar or something like that, it is not waste, but it's not a high priced commodity. They can be used properly if they can. So all this involves some kind of a refining process. The refining process means having a crude oil, converting them to the size of the molecule that you want, and value added molecules. So this is called, can be isomerization, it can be alkylation, it can be addition, whatever chemical reactions that we have studied in general organic chemistry. But it has to be done with these molecules, which is very big molecules. So therefore, the industry today insists on this. The same way, drug drug molecules. Now, drug molecules, for example, you take a hypertension molecule or something like that, boot synthesis or whatever it is, it all requires 5 to 6 steps. These things can be today with this type of materials, porous materials, we can make them in single step.
Okay.
Ibuprofen can be synthesized from a basic molecule in single step.
Okay.
Today it is produced by 5 steps or 6 steps. So the cost will come down. Cost only is not the criterion. The drugs will be easily available.
Okay.
So therefore, essentially what it means is that we have to reorient our research. We cannot succeed in one day. Okay, boot synthesis is known for decades. Now, if I were to introduce it in one step, everybody will laugh at me. But it is possible. Okay, but to economically produce, it has to be did. So like this, many things can be done. Okay,
so these are the areas that you feel that industry itself is directly interested in a research program that is ongoing.
Yes.
And also similarly, if we had research programs in those areas, more industry interaction is likely. So if you look at the students that graduate, I mean, let's say masters and PhD students when they graduate, what sort of positions do you see them getting in industry or any other circumstance?
Okay.
Of course, in general.
Our center has a peculiar place, but chemists in general, they find the opportunities in chemical industries, especially pharmaceutical industries. If he is an organic chemist, if he is a material chemist, means the material development. But today, India is in a favorable position because all multinationals have got their headquarters or semi-headquarters in India. So, for example, Shell or SABIC or anything, okay, GM, GE, whatever thing, even P&G, they are all here in India, and therefore they have opportunities there. Previously, this type of opportunity was not available for India. They have to only look for research positions abroad or employment abroad.
Yeah.
Today, equivalent employments are possible in India. So that is not a problem. As a matter of fact, chemists, I don't see any problem in the next 20-30 years.
Okay, that's a very, I think, heartening piece of information for, I think, a lot of students who are in chemistry.
Yeah, if they have the necessary inspiration, they can easily fit into any of these things.
Okay. Let's say on a more mundane note, how often do you feel, I mean, when students come and get into a master's or a PhD program, they one of the things they are often told that classroom learning is one, but interacting with peers, interacting with your advisor, interacting with your guide, these are things that actually contribute a lot to their learning process. So in your experience, what would you recommend as how often students should be meeting their guides or how that process should go?
Okay, this is one of the main issues of Indian education itself. Okay, I am sorry to tell this, but it is a fact. For example, if our learning, classroom learning is the teacher or the professor will come and give lectures. Okay, and he may not be having time to establish that it has crossed the barrier of the lecturer to the student. This is the student also is inhibited to ask questions or raise doubts. So this is a very big challenge. So what I suggest is instead of giving lectures and courses should be interactive. More interactive. As a matter of fact, questions can be on both sides. Okay, the teacher also can ask questions instead of delivering the lecture. See, previously what was bothering in the lecturing process is covering the syllabus. Now, covering the syllabus is not at all the criterion. Okay, how you have comprehended the syllabus is the question, because that is what you are going to make use of in your career. So therefore, the classroom means in a lecture hour of 60 minutes, there should be 60 questions across.
Okay.
It can be across between both of them. That is one thing that has to come in India. In Indian education, this is not at all.
This is underplayed. This is quite a bit underplayed. But what about, as a student guide interaction? I mean,
Guide here, the guide should be available on all the time.
all the time. Okay.
That is the first
Easy
thing.
accessibility of the guide is a very important thing.
And also he should treat the students equally.
Okay.
Because he should not put him in a fearful situation.
Okay.
Or respectful situation.
Okay.
That the respect should be only inherent. It should not be shown outside.
Okay. So that makes the interaction more
student should
effective.
be able to tell him what is inhibiting him.
Okay. Sure.
That is this is in Indian situation. This Guru Shishya situation is really, that is what is the Shishyan is capable of asking anything to the Guru. Guru also is capable of asking the Shishya anything. That is somehow or other in the in between this has disappeared.
Okay. Okay. So that is something that's worth reviving.
Yes.
So in a similar sort of in a related sense. There are different ways in which people measure, how students have performed in, research activities, and commonly we refer to just publications. Over and above publications, are there other ways in which you look at students to measure, how much they have evolved as a researcher?
Okay, this is one thing that in our center we are practicing. For example, I will tell you one example. Then will be, and also this example is well known. For example, when ammonia synthesis was proposed by Fritz Haber, his boss, Ernst equation. Ernst put thermodynamics and said it is impossible. So you cannot work on this. But in spite of it, Haber worked on it and got the ammonia synthesis with the BASF. That is not the criterion. If ammonia synthesis were not to be there, world population would be 1/2 or 1/3. Okay. Because it has provided the food for all the people. That is why world population has increased. Okay. So now the question is, the same question only we asked. CO2 to chemicals is non-thermodynamically possible.
Okay.
So, for example, this is the way we came to this CO2 problem. So, if Haber could do ammonia synthesis, why can't we do carbon dioxide to chemicals?
Chemicals, okay.
So, this type of questions we ask the students and make them interested in the research, because these researchers will not give results immediately. So, they should not get discouraged. They should be willing to face problems. So, like this, today the students should be motivated for this. This is only one example. Many examples are there. For example, supercapacitors. As I told you, the heteroatom substitution in carbon materials is now known. But when we started 20 years back, nobody even thought that nitrogen can be substituted in carbon, because nitrogen is a fifth valent, carbon is 4 valent.
4 valence, okay.
So such a solid state material is not possible. Even now, many solid state chemists will not agree with that.
Okay.
But that type of things are possible. So one can unconventionally think.
Okay, so you're looking for unconventional thought processes to
or induce those processes.
And that gives us a sense that they are actually thinking different from being put into a streamline, and then therefore that's something that they are learning as a research process. Okay, so that was a very interesting insight on how they have to think outside of whatever parameters they are conventionally told about, and then that helps them grow as researchers. So I would like to conclude this discussion by asking you this. I'm sure there are a lot of students out there who are considering advanced degrees in chemistry, master's degree or a PhD degree. So what are your words of advice to these kinds of aspiring students who are aspiring for higher degrees in chemistry?
Okay, chemistry is generally considered as a subsidiary science to physics and things. Physics is more basic than chemistry, like that. That is what the people think. But as I told you, the students should have, first thing is that his analytical skills have to come to atomic scale, not molar or millimolar or micromolar. It has to come to atomic scale. Now, when it is coming to the atomic scale, the probes also have to change. Okay, for example, electrochemistry, it can now do nanoscale. Okay, but what we want is picoscale or even femtoscale.
Okay.
10 to the 12 or 10 to the minus 15 molar concentrations. So now the students should have dynamism in taking up such challenging things. That is the first thing. Second thing is the chemists are always afraid of mathematics. Now today mathematics is only, even today or even everything, mathematics is only a language for non-mathematicians.
Okay.
Mathematics is pure mathematics is mathematics for mathematicians. But for all others, it is only a language. If I want to say 4, I can say 2 plus 2 is 4. So therefore, that is how it has to be. So therefore, we should
embrace it completely.
Embrace mathematics as a language for the other scientists. If they do that, then they will be able to perform, as I told you, DFT or Hartree-Fock or even self-consistent. It will become easy.
Okay.
But unfortunately, our quantum mechanics people who teach for the chemists, they immediately go to a second order differential equation and solution of them and all those things, instead of the emphasizing the physical significance of the solutions.
Okay.
So therefore, these type of things, they should not take it too much. They should look for the analytical solutions of the mathematical expressions.
Okay.
Then they will be able to perform well. So I don't think the chemistry or even physics or even natural sciences or physical sciences is a challenging job. It is a very entertaining and interesting job.
Okay.
So the students should feel
comfortable.
Engineering is one of them. I am not denying that.
Sure.
Because you are doing it hands-on. The same thing can be done. Because, for example, MOF, metal organic framework, is building a building with the molecules.
Okay.
Instead of making a building with brick and mortar. So like that, porous solids also is building a material only. So therefore, chemistry and generally science can be more interesting than what it is today.
Or what it is maybe perceived to be. Maybe people perceive more challenges than they immediately recognize the interest in it.
Yes.
And so an aspiring student, I think if they learn to distinguish that and put away their fear and embrace it in a more wholehearted way, they probably will be able to more comfortably fit into a master's or a PhD degree. Okay, thank you very much, Professor Vishwanathan.
Thank you.
It's a pleasure that we could have you. It's a privilege that we could have you in this
Thank you
discussion.
very much.
Thank you.